Okay, great. All right, so we'll begin. It's week 5. So we just have 2 weeks remaining. So we got this week is this week and next week, and so this week we'll finish up chapter 8 and do chapter 9, and then next week on Monday we'll wrap up chapter 9, and then we'll have our final exam. So it'll be next week, Wednesday will be a review session, and then the final exam will be on Friday of next week. Okay, and then and that will be it. So it's it goes by quickly. We're fitting the entire quarter in 6 weeks, and so oh, is Monday a holiday? Oh my goodness. Okay, I forgot about that. All right, well, I guess so. What do I have written in the syllabus here? Monday. Okay. Lecture 6-1. Okay. All right. Here we can do a quick. I'll do a quick poll here. Let me see. How do I do a poll? Okay, you know what? Well, there's only 34 of you. Okay, so this is what I'll do. On CCLEI, I will add a poll, and I will ask whether you want, of course, you don't, I don't know if people want it, but this is what will be the options. Okay, so let me, here, I will explain. Okay, so I can have class on Monday. It's a holiday, all right? So, okay, so Monday, September 7 is Labor Day. Okay, so this is a holiday, right? So normally would not have class, but I want you guys to get the full resources. So it's it's easier for me to just take the day off, but I also want your class to be. I want you to feel like you got everything out of the class that you were supposed to get out. Okay, so option 1 is holiday. Okay, treat it like a holiday. Okay, so there'll be no class, and then so week 6 Wednesday will be wrap up chapter 9, and then week 6 Friday. So this will be holiday, no class, wrap up chapter 9. Week 6 Friday will be final exam. Okay. And then option 2, I'll put a poll on CCLE and I'll have you guys respond this week. Will be week 6 Monday will be wrap up chapter 9. Okay, so live class via Zoom. Class is also recorded. Whatever. Okay, and then week 6 Wednesday will be a review session, and then like the other review session, this will be optional, and then week 6 Friday. Oh, on paper, this is option 2. This is what I had originally written in the syllabus. On paper, this just seems better anyway. It's a little bit more work for me, but I think presenting the wrap up of chapter 9 on Monday anyway. Whether you want to, okay. Now that I put this out, I feel like option 2 is the clear winner, but I'll let you guys vote, and if it's overwhelmingly poor, yeah, you know what we can do? We can do is just Yeah, I guess I can cancel the viewing quiz if that will make you feel better. We'll do a lecture viewing quiz if there's class on Monday. I mean, I can extend the viewing quiz. I think there will be a viewing quiz, but I'll just make the viewing quiz due like Thursday night, because you definitely need to see the stuff before you take the final exam. So, okay, so we'll make a quiz instead of the normal Tuesday or something like that. Okay. Yeah, option 2 seems like the clear winner, but I guess I could put it for a vote, and then if it's overwhelmingly that you don't want the review session or something, but I honestly don't see any drawbacks to option 2, because you can just watch it whenever. So anyway, okay. All right, we'll carry on then. What about Monday discussion? That's a good question, because I didn't think about. My computer's freezing up. All right, what should I do? I guess we'll just cancel discussion on Monday. I'll give the TAs. I can't. So yeah, Monday discussion will definitely be canceled. Okay, because actually I can't make my TAs work on their holiday. So I can choose to like volunteer to work on Monday, but I can't force my my TAs to work on Monday because that's their holiday. So Monday discussion is canceled. So that's so that will be that. Okay. I think I'm gonna go with option 2. I don't see any downside to it. Okay, because then we still have there's still a review session as optional. We're still gonna get the same content. It'll just be presented earlier, and if you don't want to show up on Monday because it's a holiday, you don't have to. You do have to watch the video at some point. So we'll do that. Is that all right? I'm just talking this through, and I feel like this is the clear winner. In that I don't think it presents much of a downside for you, in that if you want to watch Monday's thing on Wednesday and just treat Monday a holiday, that's totally fine. If you don't want to attend the review session, you don't have to, but for the students who want a review session, they can, and that will be it. All right, so all right, this is what we're going with. All right, I'll throw this on the website. Okay, anyway, sorry. All right, the other part was I'm still going to do this. I'm canceling lab 5, so there's no lab 5 for you guys. Okay, I'm going to just give everybody 100% credit for lab 5. So because that was in the syllabus that we would have 5 labs, and each one of them is worth 2%. So for lab 5, I'm going to just go ahead and give everyone 100% for that. Instead of a lab assignment, I'm giving you a reading assignment, okay? So the reading assignment, but you don't actually have to do anything for this reading assignment. You do have to read it because, well, you don't have to do anything really. But if you want, but I'm going to ask a couple questions on the final exam related to the reading assignment. So if you want to get those questions right, you have to read it. But if you're just like, well, it's only a couple questions on the final, it's not a big deal. Nobody's going to force you to read anything, right? Okay. So anyway, I thought it would be good, because the whole point of this class is to give you some statistical literacy, in that, you know, when you read articles in the future, if you read a journal article and they do a section on statistics, or everything will have a discussion of their data, and some of it will involve some statistical talk. I want you to be able to read that and understand what they're talking about. And so here's a journal article that's been made available for free. And so you will just you will read the article, and it is about hydroxychloroquine. I'm not trying to be political, okay? I know this has been in the news, but it's hydroxychloroquine as a possible treatment for COVID-19, and I'm not trying to be political or anything like that. It's just, it seemed to be relevant. It uses fairly basic level statistical analysis tools that are relevant to our course, and so I thought it would be good. And you know, again, when I say I'm not trying to be political, I do believe in science, and I guess to some degree that can be a little bit of a political statement, but you know, I'm not trying to say anything. Okay, so anyway, there's an article for you to read, and then I have some questions related to the article, and I'm going to put probably a couple of these questions in multiple choice format on the final exam. So you can probably expect maybe two questions from here on the final, and then your TAs will go over the answers probably in section on Wednesday, okay? To kind of make sure you did your reading. So hopefully you'll read this and enjoy, at least feel like you've learned something in the class, because I think a common story is that when people who have not taken statistics, when they read a journal article, will often just kind of glaze over the statistical analysis part. So now hopefully you can read that, and then when they talk about p-values, you'll understand what they're talking about. All right, so anyway, that's that, okay? Are there any questions regarding that? So there's nothing to turn in, there's no lab 5. I have the questions, but you don't even have to answer them. They're for your own benefit, and I'm just warning you that maybe a couple of those questions will appear on the final exam, but there's nothing to turn in, okay? As far as today's discussion goes, I'll have the TAs go over homework questions, or you can ask any other questions. You can ask for help on the last week's lab. And then for Wednesday's discussion, they'll go over the questions from the reading. Okay, any questions about that? Great. Then we will get into today's topic, which is we're going to do a conceptual deep dive on hypothesis tests. So on Wednesday of last week, we introduced the hypothesis test to see if a population proportion is equal to some value. And what I want to do is I want to get a little bit more into the conceptual part of that, and then we'll expand that to do a comparison between two proportions. All right, so when we set up the hypothesis test, the null hypothesis said that the null hypothesis makes a claim about the population. It will state that the proportion in the population is exactly equal to some kind of quantity P0, and that's the statement that we make in the null hypothesis. It's always P is equal to some number, and we call that number P0. And what we do is we test that hypothesis that the population proportion is equal to some number, like 30% or 20.2% or whatever it is. We test that against our data. And the way we do this is that we calculate the p-value. And the way we've defined the p-value is that it is the probability of observing the data, observing our data, or something more unusual if the null hypothesis were true. So if the null hypothesis were true, we would expect our data to reflect whatever the null hypothesis is saying. So if the null hypothesis says that the population proportion of seniors is around 20.2%, when we take a random sample of people, we expect around 20.2% of them to be seniors. Of course, because of random sampling, it's a little bit higher or a little bit lower, and we want to kind of find the probability of getting whatever we observed in our sample. And the conclusions we will make is that based on the p-value, if the probability of getting our sample is small, okay, meaning our p-value is less than alpha, we would say this is a low probability. Therefore, the fact that we observed this data tells me that my null hypothesis, my initial assumption, is wrong. Otherwise, how do I explain getting the data that I have? Or on the other hand, our p-value could be greater than alpha. And in that case, we say our p-value is large. And then we say, well, the data that I have would not be considered unusual under the null hypothesis. It might not be exactly what the null hypothesis states, but it's also not that unusual. And so right now, I have no reason to question the null hypothesis. It doesn't prove that the null hypothesis is true, but we have no reason to question it. Okay, and so, okay, these are the kind of the fully expanded out conclusions. So the p-value is small, meaning our probability is less than alpha. That means whatever test statistic we observe, the test statistic for our data, is considered to be extreme if we assume the null hypothesis to be true, right? So if the null hypothesis states that the proportion of seniors is around 20.2%, and we end up selecting a sample that's 32% seniors, okay? If the null hypothesis were true, it would be very unusual for a sample, a random, truly random sample, to end up being 30.2% seniors. All right, so the fact that we actually did observe this data where 30% of the people are seniors indicates to us that the initial assumption that the proportion of seniors in the population is only 20%, that initial assumption has to be wrong. Because how else do I explain the data that I got, right? Because this actually happened. And so with a small p-value, our decision will be to reject the null hypothesis. And this statement is just as important. It's not bold, but technically it is possible that the null hypothesis is true and that we just happen to get an unusual result because of random coincidence. So technically it is possible that the population is only 20% seniors, and just by random coincidence, random sampling, we happened to get a sample where it was 30% seniors. But the probability of that is so small that we're just kind of willing to kind of ignore it and discount it and say that that's not the case. We're willing to reject this possibility because the probability of our result is small. On the other hand, if the p-value is large, right, that means that our observed data can be easily produced by randomness while the null hypothesis were true. So perhaps our random data is 23% seniors, right? We take a random sample and it's 23% seniors. Our null hypothesis says that the population is only 20% seniors. So when you do the comparison and maybe you do the math, it turns out that, yeah, by random chance, even if the population were only 20% seniors, it's possible that just by random chance, you get a random sample where it's 23% seniors. All right. So even if our data does not match the null hypothesis exactly, the difference is not considered to be an unusual outcome. And so when we have a large p-value, our decision will be not to reject the null hypothesis. And it is important, and at least I emphasize this difference, is that when we say we do not reject something, that does not mean we accept the null hypothesis. So saying that we did not reject the null hypothesis does not mean we've accepted the null hypothesis. We can only say that we have not rejected it. All right. So here is an example. The null hypothesis here is that I have a fair coin. Okay, the coin is fair and will land heads with probability 0.5. Okay, sorry, I've got a question here, and it says, does rejecting, all right, so here I said, if we did not reject the null, we cannot say we've accepted the null, okay? But if we've rejected the null, does that mean we've accepted the alternative? And the answer is yes. If you reject the null, that means you have accepted the alternative. So the flip side is you can state when you do reject the null, you've accepted the alternative. But not rejecting the null does not mean we've accepted the null. All right, so the example is I've got a coin. My null hypothesis is that it is fair and it will land heads with probability 0.5. The alternative is that the coin is somehow unfair, not balanced, or whatever it is, and it will land heads with a probability of something different from 0.5. And so the fact that it says it's different means I'm going to use p not equal to 0.5, p not equal to 0.5. With this, I'm going to flip the coin 20 times, n is equal to 20. And if the null hypothesis were true, right, meaning that if the coin were fair, I would expect to see 10 heads out of 20. All right? And so with this, I can go ahead and I can calculate my p, which is 0.5, and I can also calculate my standard error by doing p times 1 minus p over n. Right? The p here is technically p0. It's the p that appears in the null hypothesis. And so we're going to just do a couple calculations that will show what kind of test statistic and what kind of p-value we would get for different outcomes. All right, so again, when I flip the coin 20 times, with a fair coin, I would expect to get 10 heads. So if I get a sample where we have 10 heads, okay, then our p-value is going to be equal to 1, right? Because a fair coin will produce a sample with 10 heads or something more unusual 100% of the time, right? Because 10 is the, quote, least unusual observation you can get, right? So when I flip the coin 20 times, I'm expecting 10 heads, and if I get 10 heads, then that is exactly what I expect. Anything different from that, whether I get 9 heads, 11 heads, 12 heads, 8 heads, whatever it is, would be considered more unusual. And so my p-value, which is the probability of getting my data or something more unusual, my p-value will be 100%, right? If I do my calculations, my p-hat is 0.5. My z-score for p-hat is 0, because p-hat minus p is 0. Divided by whatever my standard error is, it's still 0. And if I look up 0 in the normal table, I'm going to get 0.5, and 2 times that is 100%. So my p-value is 1 or 100%, because I will get something equal to 10 or something more unusual 100% of the time. And so my p-value is equal to the total probability on the right and the left, and I get a p-value of 100%. So if I flip the coin 20 times and I get 9 heads, our p-value is still going to be quite large, because the question is, what is the probability of getting our data, 9 heads, or something more unusual, which means 9 heads or something less than 9, plus 11 heads or more than 11, okay? Because 9 is basically 1 away from what I've expected, right? So if I flip the coin 20 times, I'm expecting to get 10 heads, and I got 9. So how different is my observed data, 9 heads, from what I expected, 10? So when I do my calculations, my p-hat is 0.45. The difference between p-hat and the expected value of 0.5, p-hat minus p, is 0.5, and I divide that by my standard error. My z-score is negative 0.447. And if I double that tail area, I get around 65%. So that means by random chance, I'm going to get 9 heads or less, and something more unusual, because it's a two-sided, would also mean getting 11 heads or more, right? Well, that's 1 away from what we expected. So nine heads or less, plus 11 heads or more, and the total probability of that is going to be around 65%. This is technically an approximation of the true answer because we're using the central limit theorem where I'm approximating the true answer using a normal distribution. The true answer is technically follows a binomial, and we could do the calculations, but the central limit theorem is useful to kind of speed things up and make our lives easier. So as we get more and more unusual, okay, so the total area is this purple and lime green area. And so we still are coloring quite a bit in our map here, or in our picture. But we're going to go a little bit farther away. We're going to say, what if I only get 7 heads? All right, so I went ahead and I skipped from 8 heads because it would have just been more of the same. So we're going to go down and say, what if the coin landed heads only 7 times, right? So at what point do we question that this coin is no longer a fair coin, right? So if I flip the coin 20 times, I'm expecting around 10 heads. If I got 9 heads, I wouldn't question that it's a fair coin. If I got 7 heads, would I question that it's a fair coin? So we can do the calculations for 7 heads. The calculations for 7 heads, the p-value ends up being around 18%, right? So if I do my calculations, my p-hat is 0.35, my z-score, which is p-hat minus p0 divided by the standard error, that ends up being negative 1.34. And it says that, you know, when you flip the coin 20 times, you're expecting to get 10 heads, and this time you only got 7. Is that proof that the coin is unfair? And we would not say that it's proof that the coin is fair, or it doesn't support that the idea is that the coin is unfair, because you can get 7 heads out of 20 flips, and that's going to happen around 18% of the time, right? 7 heads are something more unusual, which technically is 7 heads or less plus 13 heads or more, okay? And that happens with a probability of around 18%. So this is not unusual enough for us to reject the idea that the coin is fair. It doesn't prove that the coin is fair, but it's not enough for us to reject that idea. And so here's our picture. And again, it's a two-tailed test, so we're going to take both the purple and the lime green areas. It's around 18% there. All right, so with around, what if I flip the coin 20 times and I only get heads 6 times? If I only get 6 times out of 20 flips, okay? If our significance level is 5%, then the result would not be unusual enough for us to reject the idea that the coin is fair. Because if we do the calculations, it says you can get 6 heads out of 20 or something more unusual, which means 6 heads out of 20 or 14 heads out of or more. And that's going to happen around 7% of the time. Okay, so at a 5% significance level, this is not unusual enough for us to reject the null hypothesis. But if we're willing to be a little bit more risky and we choose a 10% significant level, then we would say, well, the fact that this happens only 7% of the time means I don't think this happened by bad luck. I'm thinking this is an indicator that the coin, something happened to the coin and it's no longer landing heads at a rate of 50%. Something happened, now it's landing heads less often than 50%. So that would be if we're using a 10% significance level. Right? And so we can see, you know, as we're getting more and more farther away from what we expected, my p-value keeps going down. Right? And so, you know, the picture with only 6 heads out of 20 or 14 heads or more out of 20, the area and the tails get more and more unusual. Okay? It's quite a big drop to go from 7 heads. 7 heads has around an 18% probability to 6 heads has only around a 7% probability. All right, so the question is, why am I multiplying this p-norm value by 2 to get the p-value. Right? So the question is, so if I look up p-norm, it's going to give me this purple area. The p-norm is the equivalent of using the z-table, which always gives you the area to the left. Right? So here I've got my z-score is negative 1.78, 1.79. And if I take the area to the left, the area to the left is 0.0368. 0.0368, that's what this little diagram shows. Happens around 3.7% of the time. The way my alternative hypothesis is written is that I'm interested if the coin no longer lands heads at a rate of 50%. I'd be interested if it lands heads more often than 50%. I'd be interested if it lands heads less often than 50% heads. And so because both sides are interesting to me, I'm going to use a two-sided test, a not equal sign in my alternative hypothesis. And that is why I'm multiplying my tail area by 2, because I want both the left-hand side and the right-hand side. This left-hand side in purple represents the probability of getting 6 heads or fewer out of 20 flips. Right? So if I flip the coin 20 times, I'm expecting around 10 heads. What's the probability I only get 6 heads? Well, it's around 4%. But 6 heads or fewer is equally unusual as 14 heads or more. Okay, because 14 heads is, you can think of it as 6 tails, right? So what's the probability of getting 6 tails or fewer, or 14 heads or more? That's going to be equal. So I'm taking the tail areas and I'm multiplying it by 2. Does that make sense? All right, and if I flip the coin 20 times and it lands heads only 5 times, then my p-value is very small, right? So if I flip the coin 20 times and it lands heads only 5 times out of 20, then we might take that as evidence that something happened to the coin and it no longer lands heads with a rate of 50%. Because is it technically possible? Is it possible to flip the coin 20 times and it lands heads only 5 times out of 20 just from bad luck? It's possible, but it only happens 2.5% of the time. It happens quite rarely, right? So it's kind of just like if I have a deck of cards and I say, go ahead and name a card, and let's say you name the 5 of clubs, and I just reach in, is it possible that just by random luck, I happen to get your card by random luck? It's possible, but that happens with a probability of around 2%, okay? So it's not impossible, but the probability is quite rare that I think if I reached in the deck and I pulled out your card, you would be impressed, right? You would be impressed. If somebody did that as a card trick, you would be impressed, because the other alternative to them doing some kind of trick to get your card is that, I don't know if anybody would, if David Blaine did a card trick to you and you just go, you had a 2% chance, 1 in 52 chance of that happening anyway, I am not impressed, because you just had good luck there. I don't think people would say that, right? When the probability is quite low, something around 2%, it doesn't feel like it was a result of random chance. And that's what we're saying here. We're saying, could you get a coin to land heads only 5 times out of 20 just from random chance? It's not impossible, but it happens only 2.5% of the time. And because that probability is so low, I'm willing to ignore it. I'm willing to reject the idea that it happened by random chance. And instead, I'm going to conclude that something happened to my coin, and that is why it is not landing heads as often as I think it should. And that's kind of the reasoning. And so as your values get more and more extreme, the probabilities, the associated p-values get lower and lower and lower. And in our picture, the difference between landing heads 7 times out of 20, 6 times out of 20, and 5 times out of 20 gets the difference in probabilities, I think, is quite um, quite impressive. So, all right, are there any questions before I keep going here? Or do we feel pretty good about this stuff so far? All right. So all of our tests have been performed under the assumption that the central limit theorem can be applied, right? So our hypothesis tests depend on the central limit theorem, which says we can take the sampling distribution and approximate it with a normal distribution. And in order for us to use the central limit theorem, there's a few conditions in that the sample size has to be large and the sample has to be selected randomly. If these conditions aren't met, then technically we shouldn't be using the central limit theorem. So if the sample size is not large, then the normal distribution, using the normal distribution, might not be a good approximation of the sampling distribution. And so the result means that the p-values that we calculate may not be as reliable as we want. And, especially if the p-value you calculated is kind of on that borderline of either rejecting or not rejecting the null hypothesis. So in this case, other tests do exist that we can use when the sample size is small. And you got these permutation tests and things like that. It's a little bit beyond the scope of our course, so we're not going to bother covering them, but I do want to let you know that these do exist. And so if you are ever doing research and you encounter a situation where the conditions aren't met to use the central limit theorem, you can look up other tests that can be used. You should probably talk to somebody, maybe a statistician or somebody who's a little bit well-versed in statistics that can kind of guide you to picking the right hypothesis test to use. But there's lots of different methods and ideas that exist there. If on the other hand, the sample is not selected randomly, then we cannot generalize the findings from the sample to the general population. So when we do medical experiments, generally you're not getting a random sample. Generally the sample that you are working with will be patients from a selected hospital, patients with a certain condition. And so in order to kind of generalize your findings, the researchers have to hope or assume that the sample that they are working with is representative of the population that they are studying. So if they are looking at a sample of people in the United States, those findings can probably only be generalized to maybe the United States as a whole, but it depends greatly on that hospital or wherever that data is coming from. So if this is a hospital in, like Cedars-Sinai, which is a hospital known for treating, celebrity patients and being very expensive and people with money, their outcomes will be different from a hospital that maybe serves an underserved community or a community struggling with poverty and things like that. The outcomes that happen at different hospitals, are related to many other things. And so if a study is only conducted at one hospital, it's going to be difficult to generalize those findings to the greater population. So a lot of studies will be done where they've obtained patients from several hospitals, and they're hoping that their sample is representative of the population. But it's very difficult to do a medical experiment where you have a truly representative sample. And, with something like COVID-19, where it's a global pandemic, you will have researchers in countries around the world doing medical research, looking to see, what are some, factors that affect mortality and hospitalization, what are some factors that affect, recovery and improvement. And it's going to be different from one country to another. You know, one country might have more people who are overweight and obese. One country might have people who have more people who are, you know, with high blood pressure, different kind of diets and things like that. And so, you know, what scientists find in one nation may not generalize to the entire world population. It might. And so a lot of times it's important that other researchers try to replicate. If one study finds interesting findings, then other researchers might try to replicate the same study to see if they come to the same results. And if the study is able to be replicated across different groups, then that will support kind of the findings of the research. But research is hard. Doing good scientific research where you're dealing with a population that, or dealing with a sample that should generalize to the population, whatever population you define, is not an easy task. So, all right, but anyway, just for in our class, you know, just to kind of keep things simple, even if the sample is not random, one thing where we randomize treatments that can be used, that can still be used to draw cause and effect conclusions for the groups being studied. And like I mentioned, ideally the study can be replicated with another group to corroborate the conclusion that they've made. There are errors that are inherent to the hypothesis testing process. This is not, I'm not talking about a mistake in calculation where, you know, somebody used the wrong standard error, they used the wrong n in their standard error, or they've made some kind of mistake. Okay, that's not what I'm talking about. These are errors that cannot be avoided, as far that we cannot completely avoid, because we are making a conclusion based on a sample of data. All right, and so the fact that we don't have all the information about the population and we're trying to make a conclusion about the population based on the sample means that it is impossible to avoid mistakes, right? Just like when nobody can predict the future perfectly, and so no matter how cautious we can be, there's always a possibility that we made the wrong choice. And so that's an error or mistakes that are unavoidable. And in the same way, as far as hypothesis testing goes, we cannot avoid these mistakes. And there are two types of mistakes we can make. And the names of these are the type 1 and the type 2 error. We later came up with better names, the false positive and the false negative. But when statistics and hypothesis testing was first being researched and studied, they realized, you know, there are two different types of mistakes that can be made, and they didn't have good names for them, so they named them type 1 and type 2 error. And those names have stuck around in the literature. Later on, we came up with better names like the false positive and the false negative. So the false positive means our conclusion is that we reject the null hypothesis. The conclusion that the researcher makes is to reject the null hypothesis, but it turns out that that's a mistake. And that in reality, the null hypothesis is actually true. You know, the null hypothesis says that the proportion in the population is 0.5, that it's a fair coin, all right? So the coin is actually a fair coin, but maybe the person got bad luck and the coin landed heads only 5 times out of 20. And because the coin landed heads only 5 times out of 20, the person concludes that they should reject the null hypothesis. They didn't do anything wrong in the process. That's the correct conclusion to make if the data was 5 heads out of 20 flips. But it turned out that 5 heads out of 20 flips was just really bad luck. And our poor researcher makes the wrong mistake because of kind of some bad luck in the data collection. So in reality, the null hypothesis is true and should not have been rejected. The other type of error is the false negative. the researcher does not reject the null hypothesis, but that's a mistake. Okay, in reality, the null hypothesis is false and should have been rejected. So perhaps, you know, in another scenario, somebody has a coin and the coin is actually unfair and they are cheating. They're doing some kind of game and they're cheating or something, right? Or maybe this is the carnival game where you're spinning the wheel. The wheel should be landing to the winning spot 50% of the time, but they've actually rigged the game a little bit so that it wins less often than 50%. But if somebody plays 20 games and they're expecting to win 10 times and they only win 8 times, winning only 8 times is not going to be enough to reject that null hypothesis. And so they say, well, maybe I just got bad luck. That's the conclusion. They conclude that the game hasn't been rigged, or they conclude that they don't have evidence that the game has been rigged. Sorry, they don't conclude that the game is fair. They conclude that they don't have enough evidence that the game has been rigged. But maybe the game actually was tampered with to lower the rate of winning. And that would be the false negative. So yeah, in a little bit more detail, the false positive is rejecting the null hypothesis, but the null hypothesis is actually true. And so, you know, you might do this where your p-value, you do the calculations, your p-value ends up being 4%. If the significance level is 5%, if alpha is 5%, what we're saying is that because our data is unlikely to happen when the null hypothesis is true, meaning that there's only a 4% probability of our data happening, we're going to conclude that the null hypothesis is wrong and reject it. But it's possible that the null hypothesis actually is true and the data was just a random fluke, right? So our decision to reject the null hypothesis when in reality it was correct is called a type 1 error or false positive. Oh, sorry to interrupt, but have you given a lecture quiz answer yet? I have not. Thank you for your interruption and question and reminder, because I often forget these things. Week 5, Monday, that's today, the first letter is B. B as in bear. B is the first lecture quiz answer for week 5, Monday. All right, so that's what we have here for our type 1 error. And then the type 2 error is the flip side of this, where we do not reject the null, but in reality it should have been rejected. So maybe your p-value ends up being 7%, and because your 7% is greater than 5%, which is your significance level, your alpha significance level is 5%, you don't reject the null hypothesis. That means the data that we observed is not unusual enough for us to doubt or reject the null. But maybe in reality, it turns out that the null hypothesis is actually wrong. We should have rejected it. And so this would be called a type 2 error. The type 2 error is the false negative. This, you often make a type 2 error if you did not collect enough data. So you know, when you flip the coin only 20 times, you know, you'd have to get something around 5 heads to reject the null hypothesis. And even if you get something like 7 heads or 6 heads, you might not reject the null hypothesis. But it could be that if you flip the coin more, or if you collected more data, that you would have rejected the null hypothesis. And so that could happen, right? The other possibility is that there's a random fluke that leads you to the wrong conclusion, right? So you might actually have a coin that's unfair. The coin is actually unfair, but just by random chance, it landed heads 10 times out of 20, right? So maybe it's a coin that has been tampered with so that it lands heads only 35% of the time. But just by random chance, when you flip the coin a bunch of times, it landed heads 10 times out of 20. You go, oh yeah, it checks out. It seems like it's a fair coin. But it could just be a random fluke going the other way as well. So that would be a type 2 error, the false negative. So it could be you didn't collect enough data. It could be a random fluke going the other way. So here's a table of the results that we can make. So here is the decision that we make, either to reject or not reject. And in truth, the null hypothesis is either true or false. So if the null hypothesis is false and we reject it, that's the correct decision. That's what we want. And if the null hypothesis is actually true and we do not reject the null, that's the correct decision. It's just when the null hypothesis is true and we reject it, that's the type 1 error or the false positive. Or the flip side, if the null hypothesis is false, but we did not reject it, that's the type 2 error. So this is our table of results. I just kind of want to check in here and make sure you guys are doing okay. Are there any questions here? All right. Well, then we'll keep going here. So, and then let me talk about significance level, and then we'll take a break here. So the significance level, the alpha that we choose, we've often been choosing 5% by default. The significance level alpha is equal to the probability of committing a type 1 error. So when we say alpha is 5%, we are kind of subtly acknowledging that I could be making this mistake. I could be making a type 1 error 5% of the time. So we're accepting this kind of level of risk, and we're saying that we're okay with that level of risk. All right. So we can choose to, we might say, well, I don't want to make a type 1 error. Can I pick a different alpha so I have a lower risk of type 1 error? And the answer is yeah. You can pick a smaller alpha. And if you choose a smaller alpha, your significance level, you shrink your significance level down to 1%, you'll be making a type 1 error less often. So if you pick alpha equal to 0.01, you will make type 1 error 1% of the time, right? And what that means is that means you need stronger evidence to convince you before you reject the null hypothesis. So when my significance level was 5%, I had to flip the coin 20 times and get something like only 5 heads out of 20 to reject my null hypothesis. Let me do some quick calculations here. If my significance level is only 1%, so let's see, P is equal to 0.5, N equal to 20, standard error is equal to square root of 0.5. All right, if I do, let's see, what if I do 4 out of 20? All right, so 4 would allow us to reject it. So with a alpha of 5%, you know, when I flip the coin 20 times and I get 6 heads out of 20, I don't reject the null hypothesis. But if I get 5 heads out of 20, I will reject the null hypothesis. But if I reduce my alpha to 1%, that result of getting 5 heads out of 20 flips is still not going to be enough to convince me that the coin is unfair, right? I'll say, yeah, you know, 5 heads, that's a lot less than what we expected, right? I'm expecting 10 heads out of 20, but I only got 5 heads out of 20 flips. But 5 heads out of 20 flips, that's not unusual enough for me to reject the null hypothesis. we're saying when I get 5 heads out of 20, it's not that it's unusual, but it's not unusual enough for me to say that the coin is unfair. And if I choose an alpha of 1%, I would say, you know, in order for me to be convinced, I need to see only 4 heads out of 20. 4 heads out of 20, that would be really unusual. That would convince me. So we're basically moving the threshold to something even more extreme before we're going to make the conclusion to reject the null. That's what we're doing. So when you lower your alpha, you're saying the data has to be even more extreme in order to convince me. So it's kind of just like, you know, you get in a debate with somebody and let's say these are reasonable and rational people that you are debating, right? So if somebody came to some conclusion based on emotional experiences, then it's difficult to rationally argue or debate with them. But if you get in a debate with somebody who's rational, you might have disagreements about at what threshold will they be convinced of something, right? And so you might, with this much data, somebody might be convinced, and in order for someone else to be convinced, there has to be even more data presented to them. And these people are just operating with different levels of alpha. Okay, and so as the researcher, you get to choose what level of alpha to use. Now, most journals will only accept research where the alpha is about 5%. Most journals will only publish research if the alpha is less than 5%. But in some cases, you might want to choose a lower alpha or things like that. So whether you want to pick a large or small alpha depends on the situation and whether the consequences of making type 1 or type 2 error is worse. All right, why don't we take a break here? We'll take 5 minutes and we'll come back and I still got more to say about the significance level alpha, but I've held you here for a while, so we'll take 5 minutes and then we'll come back and finish off the lecture. Recording. So we left off talking about significance level alpha. Whether we want to pick a big alpha or small alpha depends on the situation and whether the consequences of making a type 1 error or type 2 error is worse. So here's a scenario. A patient visits a doctor for a disease screening. Okay, and so in general, we assume patients are healthy unless they show symptoms of illness, but this assumption is being challenged now that we know that people can carry diseases asymptomatic and things like that. But in general, this is, you would assume a patient is healthy unless they are showing symptoms of illness. So our null hypothesis is that the patient is healthy, and the alternative is that the patient is sick. And so ideally, everyone who is healthy will, after visiting the doctor, gets cleared and gets sent home, and everyone who's sick will receive medical attention. So, you know, maybe a better example would be like cancer detection or something like that, right? And so generally you would assume somebody does not have cancer unless they are showing symptoms. And so, yeah, ideally, if they're healthy, they get sent home, and if there's a situation that requires medical attention, that they get the medical attention that you need. Okay, so in our situation, a type 1 error, a false positive, means that a healthy person kind of gets flagged as carrying the disease and gets medical attention. And the type 2 error, the false negative, will be that a sick person, somebody who either has a disease or has cancer or something, is sent home without any kind of treatment. And so looking at these types of errors, I think we would agree that the type 2 error is much worse than the type 1 error, right? And because the type 2 error is worse than the type 1 error, we would rather make type 1 errors more often than type 2 errors. We really want to avoid making the type 2 error. And so what we're going to do is we're going to pick a large alpha. Okay, large alpha means we're going to make type 1 error a lot more often. But we're okay with that because in this situation, we would rather make false positives. So picking a large alpha means we're going to make more false positives, but we're going to have a lot fewer false negatives. And so it's only going to take a little bit of evidence to reject the null hypothesis. So this is how WebMD operates. So there's some memes and jokes about WebMD. It's a website where you kind of type in your symptoms, and the website tells back and says, you might have this condition, right? And so the joke with WebMD is that whatever you type in, it says maybe it's cancer, okay? But that's because it is working with a very large alpha. And for WebMD, the worst thing, the thing that WebMD wants to avoid is telling somebody who actually has cancer that they are fine and they don't need medical attention. They don't want that to happen. And so whatever it might be, as small as the symptoms are, the worst thing that could happen with WebMD, if it gives you a false positive on WebMD, the worst thing that could happen is somebody goes to the doctor. Maybe I shouldn't say worst thing, but a false positive at WebMD means somebody goes and visits the doctor and says, hey, can you check me out and make sure I'm healthy? And then the doctor does a more full screening. Okay. Now, it could cause problems where people who are prone to anxiety and things like that. But in general, they say that's a much better outcome. Sending a healthy person to the doctor for an additional screening is a much better outcome. We don't want that, but it's a much better outcome than the alternative, which would be somebody who actually has cancer or is sick and needs medical attention thinks they're fine. And so that's why WebMD, operates with such a large alpha. And at the same time, the consequences of a type 1 error at this point aren't bad. But you don't go to WebMD, which is operating with a large alpha, and based off of what WebMD says, you immediately start this drastic treatment like chemotherapy or getting surgery or something like that. There's a lot of steps in between, because starting, say, chemotherapy on somebody who is healthy would be a very bad thing to do, because it's a very harsh treatment. It's very hard on the body. And so so a false positive in that case would be very bad. And so there are a whole bunch of screening steps between just an initial screening, and you have biopsies and all sorts of things kind of to make sure that this is the right decision, this is the right treatment choice based on this. And so by the time doctors are recommending a drastic choice of treatment, the risk of a false positive is very low. And so so it's not that you just go on a website and then immediately you would start something drastic. Okay. So in those cases, self-exams, they say, check your body for any kind of lumps or anything unusual. And if there's something a little bit unusual, right, you maybe like you notice a mole on your skin that's just a little bit odd, they recommend you to go check the doctor, right, for something more thorough. And maybe it's going to be fine. Maybe it's an indication of something else is wrong. So all of these kind of things where you screen yourself at home are all working with a very large alpha, that it only takes a little bit of evidence for you to say, oh, maybe I should get this checked out. All right. Here's a different scenario where a type 1 error and type 2 error, consequences of these are different. So imagine a criminal trial, and the way our justice system is set up is that we assume defendants are innocent until proven guilty. Okay, at least that's how it's supposed to be. And I know, this perhaps this kind of justice is not made equal for everybody, and so there's a lot of protests, denouncing the kind of the injustice. But in the ideal scenario, this is how our our system is supposed to be set up, in that we assume defendants are innocent until proven guilty. And ideally, everyone who is innocent will be acquitted in a trial, and that everyone who is guilty, who actually committed a crime, will be convicted. Okay. Another question here. Have I given a second quiz answer? I have not given the second quiz answer. I might as well give it now, though. So I'll go ahead and do the second quiz answer. Week 5 Monday, second quiz answer is C as in cat. C as in cat is the second quiz answer for today. C as in cat for the second quiz answer. So this is our ideal scenario. Everyone who is innocent is acquitted. Everyone who is guilty is convicted, right? But we cannot avoid making certain errors. And so the type 1 error, the false positive, will be that an innocent person is convicted of a crime. Okay, an innocent person is convicted of a crime. And the type 2 error, a false negative, will be that a guilty person is let go. Okay, both of these are mistakes that we don't want. We don't want guilty people to go free. We don't want innocent people to be convicted. Okay, these are both, we would say, that the justice system has failed in these situations. Which error is worse? And this part is always a little bit up for debate, but we would say, the way our system is set up is that the type 1 error is worse than the type 2 error, that it is worse to convict an innocent person than to let a guilty person go free. And so in that case, we say we should pick a small alpha. Because alpha is related to the type 1 error, we really want to lower that alpha to be as small as possible so that we avoid the type 1 error. And so when a judge tells a jury, charges the jury, before they go into deliberation, is that they will say, before you convict, there needs to be enough evidence that convinces them beyond a reasonable doubt. Okay, that's kind of the phrase, beyond a reasonable doubt, which indicates that they should be working with a low alpha, that they don't say use a low alpha in your decision making, but they say, beyond a reasonable doubt, which means they don't want the jury to convict based on gut feelings and a hunch, but that there needs to have been, enough evidence beyond a reasonable doubt to reject the null hypothesis. It is impossible to have alpha equal to 0. So, you could imagine maybe in some cases you'll have a bench trial where the judge will be the one to make a decision, and perhaps there's a scenario you can imagine a judge finds out that they convicted somebody who was actually innocent, and says, well, I don't want to make that mistake again, and I want to avoid ever convicting an innocent person again, meaning that judge wants to have an alpha equal to 0. But the only way the judge can completely avoid type 1 error would be to never convict anyone, right? Because there's always going to be a small risk that one of the convictions are wrong. Well, anytime the judge convicts a defendant, there's a possibility that was the wrong decision. And so the only way to completely avoid a false positive, meaning sending an innocent person to prison, would be to never convict anyone. This is one of the primary arguments against the death penalty, in that, executing an innocent person would be a terrible mistake. And so the only way to truly avoid ever making a mistake like executing an innocent person would be to never execute anyone. That would be the only way to avoid type 1 error completely, is to have alpha equal to 0. Okay. As far as regular trials and convictions go, the only way to we don't actually want alpha equal to 0. Alpha equal to 0 means that no one will ever be convicted. and I think that would be a bad system. But we do want a low alpha because we do want to avoid type 1 errors. Here's a little bit of statistics humor, I guess. And so your null hypothesis would be that the patient is not pregnant. So the false positive would be telling the man that he's pregnant, or telling the woman who is obviously pregnant, not pregnant, would be the type 2 error. So medically speaking, a type 2 error is worse, meaning that a person who's actually pregnant doesn't know that they are pregnant and may not be getting the treatment that the medical attention they need. But in a conversation with a friend or somebody you know, making a type 1 error would be considered to be a very bad error, to assume somebody is pregnant if they're not. That's okay. I guess that's your humor for the day. All right, let's talk about the one-sided and two-sided alternatives. So we can select a one-sided or two-sided alternative, meaning that we're going to have the less than or greater than sign for the one-sided or the not equal sign. And that decision is based on how the question is written. So the question asks if the data provide evidence that the proportion is greater, more, etc. We would pick a one-sided alternative with a greater than sign. And the p-value will be equal to the area to the right of the test statistic. So you'd have to find your z-score, and then you go to the table and you take 1 minus the area to get the area to the right. If you see things like, do we have evidence that the proportion is less than, lower, or things like that, then you'd use the less than sign, and you want the area to the left. Your p-value is going to be equal to the area to the left. And if you have if the question asks, do we have evidence that the proportion has changed or is different, not the same, or things along those lines, then we select two-sided alternative. We'd be interested in situations where the proportion has gotten larger or the proportion has gotten smaller. And so our p-value in these cases will be 2 times the tail area, or the 2 times the area beyond the test statistic. So it's the area to the left when z is negative, or the area to the right if z is positive, and you take that tail area and you multiply it by 2. There is a possibility to actually get, quote, the wrong side, the wrong one-sided alternative. And in these situations, you would get a p-value greater than 0.5. So let's say, we're doing this example where in the last census, the proportion of seniors in the population is something like 22%. All right. And we're interested if there's evidence that the proportion of seniors in the population has increased since the last census that we've taken. And so maybe in your data, you take a sample of 200 people and you find that 40% of them are, or 40 out of 200, not 40%, 40 out of 200 are seniors. So when we set up our hypotheses, the null hypothesis is that the proportion in the population is 22%. And the alternative is that this proportion of seniors has increased, meaning that p is greater than 22%. But then when we do our calculations, our sample proportion, our p hat, is only 20%. And so if we look at this question, does our data provide evidence? Does our data provide evidence that the proportion of seniors has increased, that has gotten higher than 22%? Our answer is no, right? Our data says that when we took a sample, we only got 20% seniors. That's not going to provide any evidence that the proportion has increased from 22% to anything higher. If anything, it might be evidence that it has decreased from 22% to something lower. So whatever our p-value is, when you end up on the wrong side, in this case, where your data shows kind of the exact opposite of what your alternative is hoping for, in that case, your p-value is going to be over 0.5. At that point, you don't even have to carry out the calculations, but you could. So in our case, if I carry out the calculations, I get a z-score of negative 0.68. And because my alternative has a greater than sign, I take the area to the right of z, which means I end up getting a p-value of 0.75. Okay, it's not necessary to even carry this out because I know my p-value is going to be over 0.5, which means I'm definitely not going to reject my null hypothesis. The decision to use a one-sided alternative, either a greater than or less than sign or a two-sided alternative with a not equal sign, should be done before we look at the data. And it's kind of considered cheating if you try out a whole bunch of different hypotheses after looking at the data in order to kind of change the p-value that you get. You know, if you have a giant set of data, it's almost, you can almost certainly find a set of hypotheses that will produce a small p-value, or you can end up rejecting the null hypothesis. But picking your hypothesis this way is not a good idea because you're more likely to end up highlighting some kind of weird oddity that just happened to appear in your particular data set and not something that will generalize to the population. All right. So I have a little comic that illustrates this, I guess a little bit more statistics humor here. All right. And so let me zoom in a little bit. All right, and so the comic says, jelly beans cause acne, scientists investigate. And the scientists come back and they say, we found no link between jelly beans and acne. The p-value is greater than 0.05. And they say, that settles that. And then the person says, I hear it's only a certain color that causes it. So they go, scientists. And so they go and they say, we found no link between purple jelly beans and acne. P-value greater than 0.05. We found no link between brown jelly beans and acne, p-value greater than 0.05. No link between pink jelly beans and acne, p greater than 0.05. No link between blue jelly beans and acne, p greater than 0.05. No link between teal jelly beans and acne, p greater than 0.05. And it goes on and on and on. No link between salmon jelly beans, red jelly beans, turquoise jelly beans, magenta jelly beans, yellow jelly beans, and acne. Each of these tests individually have a p-value greater than 0.05. We found no link between gray jelly beans and acne, p greater than 0.05. No link between tan jelly beans and acne, p greater than 0.05. Cyan jelly beans and acne, p greater than 0.05. We found a link between green jelly beans and acne, p less than 0.05. We found no link between mauve jelly beans and acne, p greater than 0.05. And it keeps going. No link between beige jelly beans, no link between lilac, black jelly beans, peach jelly beans, orange jelly beans. All of these have p-values greater than 0.05. But of course, with all of these studies being done, the conclusion, the news that gets reported is that green jelly beans linked to acne, 95% confidence, only 5% chance of coincidence. And so, you know, the issue here, it's not that anybody did any of their studies wrong. It's just that when you test out a whole bunch of hypotheses here, okay, and the author of this comic intentionally have them perform kind of 20 different hypotheses here. You know, even though the p-value came back less than 0.05, in the context of seeing all of these different hypotheses being tested, we can recognize or see that, you know what, this result could just be a random coincidence of something odd happens to our sample of jelly beans, right? Our sample of data. And we're just identifying something a little bit unusual in our data and not something that actually exists. As this is not a relationship that necessarily holds up in in the general population. So that's what we have. There's another comic. This one a little bit less, but this is kind of a joke about, you know, to get published, is something significant, you know, less than 0.05. So 0.049 and 0.04 we consider significant. Less than, even lower than that, somebody might say highly significant, and all of this stuff will be kind of on the edge of significance or suggestive significant at p level, alpha, you know, 10% level. So, you know, as statisticians, we will almost never say that the data prove some conclusion, right? At best, if we say we reject the null hypothesis, we'll say that we have evidence that support the alternative hypothesis, okay? So when we reject the null, we do say we accept the alternative, or we say we have evidence to support the alternative, okay? But if we don't reject the null, okay, all we can say is that we do not have data to reject the null hypothesis, right? We want to be careful, and we never want to say that we accept the null hypothesis, and we'll never say that we have evidence to say that the null hypothesis is true, or something like that. All at best we can say is that there's no evidence to support the alternative. Or not, we shouldn't say we have no evidence to support the alternative. We have no evidence to reject the null hypothesis. Okay. There is a distinction that I want to make between statistical and practical significance. Okay. So statistical significance just means that we've rejected the null and that the data we observed is unlikely to have happened by random chance if the null hypothesis were true. Okay, so statistical significance is kind of is something that we can calculate based on kind of probability. But being statistically significant does not mean that it is practically significant. Practical significance means that the result is actually useful, practically useful or meaningful. And this can only be assessed by someone who's got knowledge of the subject matter. So if you're a statistician and you don't know much about the subject at hand, you would not be able to make a judgment regarding practical significance. So for example, you might have a farmer who is considering investing in a new farming system and maybe this new system can reduce the proportion of unsellable produce, right? So, you know, every time, you know, when the farmer works, so some of the crops come back ugly and they can't sell it, right? Because as consumers, when we go to the grocery store, there's a strong preference for picking fruit and produce that are pretty and shiny and good looking, and things that are ugly, people tend not to buy. And so perhaps there's a new system that the farmer's considering, and it's going to reduce the proportion of unsellable produce from 8% to 5%, okay? And maybe during a trial run, the new system reduces the amount of bad produce from 8% to 6%, okay? And that this difference is actually statistically significant, that the difference going from 8% down to 6% couldn't have just been a result of random chance. Maybe it is statistically significant, okay? However, according to the farmer's analysis, this reduction going from 8% to 6% is not going to be enough to justify the investment cost of the new system, right? So the new system, you know, requires purchase of machinery and all sorts of equipment and stuff like that. And maybe it's not enough to fully justify the cost involved, right? That kind of decision requires knowledge of the finances and the market and kind of the process that, you know, just the pure data cannot reveal to us, right? So the statistics can only tell you that this difference from 8% to 6% is unlikely to have happened by random chance alone, but it doesn't tell you anything about kind of the decisions that have to be made, the finances and all of that. And so, so you need somebody who's knowledgeable on the subject matter itself that can use kind of the data. So the statistician, the data scientist can say, hey, this could be a result of random chance, or it might not be a result of random chance. And that has to be used in conjunction with the knowledge of other parts to make a good decision. So just because something is statistically significant does not necessarily mean that it is practically significant. So that's something to keep in mind as well. So you might see studies being published on some kind of medication that is effective on a statistical level, but maybe on a practical level, it might not be worth it. Okay. All right, so I'm going to introduce hypothesis tests for two proportions. This is going to wrap up chapter 8 for us. And I'm going to kind of work through this part quickly. And I mean, the last 20 minutes of our class we'll do this. And I'm hoping that by fleshing out all of the details and going over all of this conceptual stuff, that transitioning to the two proportion hypothesis test, or the two proportion z-test, is not a huge leap. Okay? So this harkens back to kind of our days in probability. And when we were talking about probability, we had questions like, are these two events independent or not, right? So we said, if they're independent, then the probability of A given B is going to be equal to the probability of A given not B. That's what we said when we covered independent events. And so we asked a question like, is the proportion of truck owners in California, which we would find by doing probability of truck given California, is that proportion the same as the proportion of truck owners in Texas, probability of truck given Texas? And what we said is that if those proportions are the same, then they are independent. And if they're different, they are not independent. We did another example where, if is a proportion of people who wear glasses, left-handed people who wear glasses, the same as a proportion of, is a proportion of glasses wearers who are left-handed the same as a proportion of non-glasses wearers who are left-handed? And if those proportions are the same, they're independent, and if they're not the same, they would not be independent. Okay. But the question now that we want to ask is, when we get something that's different, when we get different proportions, could that different proportions be a result of random chance, right? Could the difference in proportions be a result of random chance? So this is I think the exact same slide I showed you back in that lecture on chapter 5. And we said the proportion of truck drivers from Texas is 420 out of 1170. Proportion of truck drivers in California is 470 out of 1575. We got different proportions, therefore they are not independent. And this is what we did for the left-handed and the wearing glasses. And we said proportion of people who are left-handed who wear glasses, 6 out of 60 is 0.1. Not left-handed, 14 out of, left-handed out of people who don't wear glasses is 14 out of 140. And we said these two things are the same, 0.1 is equal to 0.1, so therefore they are independent. Okay. But again, what we want to do now is we want to allow for a little bit of randomness. And so, so one idea is that the populations, we could have two populations that actually have the same proportion, but because of random samples, because of a random selection, we end up getting samples with slightly different proportions. And so now what we want to do is we want to do a z-test to see if these proportions are statistically significantly different, or is it possible that their populations have the same proportion? So in this example, we're going to ask, does my lucky charm work? Right? So perhaps I have a lucky coin or a lucky charm, and I'm going to use it when I play games at the casino. And we're going to ask, is winning or losing at the casino independent of carrying my lucky charm? And so let's say I go and I play a whole bunch of games, right? So I'm going to play 50 games at the casino, and we're going to just count how often I win. And so when I had the lucky charm, I won 26 games out of 50. And when I didn't have the lucky charm, I only won 20 games out of 50. And so when we compare proportions, I have 52% versus 40%, right? So, and kind of back in chapter 5, we would just look at these two proportions and say, well, these proportions are different, therefore they are not independent, that they are, that having the lucky charm and winning is not independent, or are not independent, that the win rate is different. But now we want to ask, are these proportions significantly different? Okay, does this data provide evidence that the lucky charm actually works? So we set up our hypotheses in a way to compare the proportion of wins, right? So the hypotheses are always about population proportions, and we're going to say we have two proportions that we're looking at. The proportion of wins when we have the lucky charm, that's P1, and we have the proportion of wins when we don't have the lucky charm, and that's going to be P2. The null hypothesis is that the proportions P1 is equal to P2. Having the lucky charm will have no effect on the proportion of wins. That's the null hypothesis, that these two probabilities, the proportion of wins, are equal whether we have or don't have the lucky charm. Okay, that's P1 is equal to P2. The alternative is that the lucky charm actually works, meaning that the proportion of wins with the lucky charm is greater than the proportion of wins without the lucky charm, that P1 is greater than P2. Okay, so this is the alternative. And so that's what we're going to test out. And so I'm going to use alpha equal to 0.05, and I'm going to kind of check my conditions. And the large sample condition here is that I need to have at least 10 successes and 10 failures for both samples. So in our case, I have 26 successes and 24 failures. Both of those numbers are greater than 10. For sample 2, I have 20 successes and 30 failures, and both of those numbers are greater than 10. So this condition is met. Our samples are random, so we're fine. Are the samples independent of each other? And the answer is yes, they are independent of each other. And so our usage of the lucky charm is random, and so what results are different, and this observations within the sample are independent. Okay. All right. So this is how the calculations work. So first, we find the sample proportions, which comes just straight from the data. We won 52% of the games for P1, P hat 1. And P hat 2, we won 40% of the games. So with the lucky charm, we won 52%. And without the lucky charm, we won 40%. And now what we also have to find is the overall P hat. What's the overall proportion of winning, whether or not I had the lucky charm? And so I add together the total number of wins. I won 26 plus 20. I won a total of 46 times. And I played a total of 100 games. So that's a total overall proportion of 46% win rate. So overall, I won 46% of my games. And that kind of just combines the total wins out of the total games played. And now I find the standard error, right? The standard error is just given by this formula. This is just a new formula that we need to use for the standard error in this scenario, which is P hat times 1 minus P hat. And I combine my two proportions, 1 over N1 and 1 over N2. And I have 0.46 times 1 minus 0.46. And this is the data standard error that I have, right around 0.1, a little bit less than that, 0.0997. And so my test statistic when I'm comparing two proportions is going to be P hat 1 minus P hat 2. P hat 1 minus P hat 2 divided by the standard error. So with the lucky charm, I won 52% of my games. Without the lucky charm, I won 40% of my games. So that's a difference of about 12 percentage points in win rate. And then my standard error is right around 0.1, 0.0997. And so my z-score ends up being around 1.2. And so I'm going to look up the z-value in the t-table, or in the z-table to get my p-value, right? So because my alternative hypothesis has a greater than sign, we want the the area to the right of z, okay? So P, and the alternative is P1 is greater than P2, so we use the area to the right of z equal to 1.2, and when you do that, you get a p-value of 0.1151. So my p-value is 0.1151. And if my alpha is 5%, my p-value is greater than alpha, so I do not reject the null hypothesis. And so my conclusion is that even though I won 52% of the time with my lucky charm and I only won 40% of the time without it, this difference of 12 percentage points is not statistically significant. This difference of 12 percentage points could have been the result of just random coincidence and not necessarily evidence that the lucky charm is actually increasing my probability of winning the games at the casino. Okay, so we conclude that we don't have evidence that the lucky charm increases my probability of winning casino games. So, so I think this is kind of a neat or an interesting follow through of checking for independence, right? So back in chapter 5, we just kind of compared proportions. And in chapter 5, we would have said, oh yeah, these two things are not independent. And because I got 52% is different from 40%. But now in this chapter, we're now accounting for differences caused by random chance. And here, we're not saying that they are independent, that the lucky charm is ineffective. We're not saying that. We're just saying we don't have evidence that the lucky charm is effective. Right? There's a distinction there. That we're saying this difference of 52% versus 40% could have just been a result of random coincidence and not necessarily that the lucky charm is actually working. Okay, we cannot say that the lucky charm definitely does nothing. Maybe if we collected more data, it would show up that it does have some kind of effect. But what we're saying is that this difference, 52% versus 40%, could have been the result of random coincidence and nothing else. So who knows, okay? So we're not rejecting the null hypothesis. All right, how do we feel about all of this? Is this okay? It's kind of a lot. Let me give you the last quiz answer for today. Last quiz answer for today is E as an elephant. E as an elephant. That's the last quiz answer for today. All right, do we have any questions? Okay, well, we'll end here for today and have a good rest of your day. Again, no lab, and I'm going to go ahead and go with this, and I'll post up the results here. Okay, for what's going to happen next week. Second quiz question was okay.